Hi, Geometry. This is Unit 3, Lesson 5, page 344. So we're going to be taking some notes on this page. We really don't need number 2, 3, 4, or 5. So notice I just lightly crossed them out with a line. So let's start at the top. It says here's triangle ABC. So A, B, C. And M and N are the midpoints of the two sides. And I can also tell that because this is marked congruent to this segment, and this is marked congruent to this segment. So I can see that N is the midpoint of the top side here, and M is the midpoint of this bottom side. So number 1, it says, convince yourself that triangle ABC is a dilation of triangle AMN. AMN is the little one. So it's saying that this is the original, and that ABC is a dilation of this original. So the big one is a dilation of this little one. What's the center? Let's mark that A. And what's the scale factor? Let's mark that B. So let's consider that for a moment. So in other words, this is my original triangle, and it grew to this triangle right here. So it looks to me like, for instance, this line is parallel to this line, and M grew out to BC. So A then would be my center. Everything's growing out from A. N, this is really considered N prime, if you will. If this is where M was, this is where M prime moved to right here. Everything grew out from my center A. So for A, what is the center of my dilation? The center is A. And so NM, this segment right here, dilates to CB. So then it wants to know the scale factor. Well, I can see that these two are congruent. And so C is twice as far from A as N is. And here B is 2 times as far away from A as M is. So it looks like my scale factor was 2. This is twice the distance from A as N. So my scale factor would be 2. And I noticed that because I noticed that AN was equal to NC. So that means it's twice as big. So the fact it was a midpoint helped me figure that out. So what we really have here with MN is something called a mid-segment. So either in this white space underneath 2 or in the white space underneath 3, I'd like you to have a couple bullet points. MN is called a mid-segment. And a mid-segment connects the midpoints of 2 sides of a triangle. So this is called a mid-segment. So we have something in geometry called a mid-segment theorem. So let's write down our mid-segment theorem. The mid-segment connecting, I'm going to push this up a little bit. The mid-segment connecting the midpoints of 2 sides of a triangle is parallel to the third side and 1/2 the length of the third side. Okay, so let's look at our particular diagram and see what is going on there. So This is telling me that the mid segment connecting the midpoints of two sides of a triangle, that's my MN, is parallel to the third side. So this would be parallel to this. And that makes sense to me. We just learned in the last lesson that a dilation, let's remember you guys, a dilation takes a line to a parallel line or itself. So in this case, it makes sense to me that if this is the dilation with center A and a scale factor of 2, like we decided above, that these two would be parallel. Okay, great. So it's parallel to the third side and half the length of the third side. Well, that also makes sense to me as well, because if my scale factor was 2, that means that my new side should be double my original side. So that makes sense as well. So in this picture, and let me move down for my notes, we know two things. One of the things that we know is that MN is parallel to BC. We just talked about that. And we know that MN, that's my little side, is equal to half of BC, or you could think about this as 2 times MN is equal to BC. So let's go back up to my two triangles and look at these two things in the picture. So we've already looked at it being parallel. Let's look at the length of it then. So let's pause for a moment and let this side right here, let's call this 9 inches. Let's say this side right here is 10 inches. And let's say AM is 11 inches. So this is my little triangle and it's dilated out to my larger one. It makes sense to me that if AN is 10 and NC is also 10, remember they're congruent, that this entire side is 20. Okay, and then if this is 11, and I see a single tick mark, so this is 11, then the entire side AB is 22. So now that leaves my NM. If this is 9, it makes sense that this is 18, because remember what happens. My image side is equal to my scale factor, K, times my original. So in this case, that would be 2 times 9, or 18. So I can see that my sides are in proportion. In my original, my sides were 9, 10, and 11. And in my image, my side lengths all doubled to 18, 20, and 22. I'd like to remind you guys, let me grab a different color, that my angles are still congruent. So A is in the little triangle and in the big triangle and is congruent to itself. N in the little triangle would be congruent to C and the big triangle, they would correspond. And M in the little triangle would correspond to B in the big triangle, and they would be congruent. Because, I'm going down to the bottom of my page, you told me right here that it's a dilation. The two triangles, the big triangle is a dilation of the smaller one. So I know my two triangles are similar. So we know that triangle AMN, the original, is similar to the new triangle ABC. So I know that my sides are in proportion. My sides are in proportion. We've been talking about that every class period. And I know that my angles, my corresponding angles, are congruent. That's what I know about similar triangles. So this is a very specific situation that you will only use when you're given midpoints. So please remember that. Refer back to this page and use this page only when you're given midpoints. You're only going to use the mid-segment theorem when you're giving midpoints of the sides of a triangle. So going to 5.3, the next page, notice that this is not the mid-segment theorem. This is not the mid-segment theorem, because we're going to see in just a moment that M and N are not the midpoints of AB and AC. So let's take a look at what's going on here a little bit farther now. Here is triangle ABC. A, B, C. M is 2/3 of the way from A to B. And N is 2/3 of the way from A to C. So if you wanted to split this up, this is like 2 parts to 1 part, and the whole thing is 3 total parts. So this is 2/3 of the way, and this is 1/3 until you get to the entire distance. Okay, so it says, what can you say about segment MN compared to segment BC, and provide a reason for your conjecture? So this is going back to something we learned in the last class. In this case, if they are a dilation of each other, A would be my center. A is the center of my dilation. So what's my scale factor? So if my original triangle was AMN, then my triangle got bigger. If my original triangle was ABC, then my triangle got smaller. So why don't we say that ABC came first? ABC is the original. So if ABC is the original, then ABC would be similar, triangle ABC, to triangle AMN, and my scale factor would be 2/3. This side is 2/3 of the original. M is 2/3 of the distance from A that B was, and B is my original. And remember, when my K is a value between 0 and 1, then I have a reduction and my shape gets smaller. And you can see that AMN is smaller than ABC. So then the last thing I want to also mention is that if this is a dilation with center A, that MN and BC would be parallel, because a dilation takes a line to a parallel line or itself. So in this case, I know that MN is parallel to BC because MN is a dilation of the larger BC with center A and scale factor, running out of room here, and scale factor K equals 2/3. It shrank. So I want to talk about the itself part of this, by the way. We haven't really talked about that very much. So the itself part of it would be like AC. So this is AC. And when I dilate AC by a scale factor of 2/3, I come back to N. And this segment is itself. AN is not parallel to AC. It's the same exact line. Up here, AB is my original side. And after I did my dilation, I reduced, it was a reduction, and now I get to AM as my image side. So AM is not parallel to AB. It is the same side. So this first part of dilation takes a line to a parallel line. MN and BC are an example of that. BC is my original, and when I dilate, it takes it to a parallel line, and MN, which is 2/3 of the original. And then this is an example of the itself, or itself. It shrank. So let's talk a little bit about the equation we've been using some, where the image is equal to the scale factor times the original. So let's just pick out a number up here. I'm going to pick out one divisible by 3 to make our math easy. But let's say that BC was 18. I can find the length of MN. So in this case, if I put the image is what I want, that's MN. If I put in my scale factor 2/3 times my original BC, which is 18, I would see that this cancels to 6, and I would end up with 12 units. So I know that in this picture, MN would be 12 units. It's 2/3 of the original. Okay, that would be the end of our notes for lesson 5. Thank you very much.